Hello everyone. I'm Maciej Korzeniowski. My name did appear on the program. I'm here to talk about simple fractals with iterated function systems. I'll spend a couple of minutes just about talking about my background, how I came to find out about fractals, what got me interested in them, and what were my first early explorations into this very interesting field. So on Twitter, you can find probably the best way to contact me is on Twitter as MatrixCat. My real name is a little bit difficult to pronounce. So I've started my first contact with a computer at about the age of 6 with a Commodore 64. This was back in 1983. A little bit fast. I've used BBCs, which are, I don't know, those of you who can spot the logo on my T-shirt. I kind of, sorry, a little bit nervous, as you can probably see. It's okay, go back for a second. Right, so I initially started at the age of 6 on Commodore 64. Tried some programs after playing games. That was my thing to initially. At about the age of 12, I started trying to expand my knowledge about computers into C and Pascal. It was about that time when I saw my very first fractal, which was from an Acorn User magazine from 1986. I actually saw that magazine quite a few years later, but I was just fascinated by how you could create such a detailed image. I don't have any further exploration pictures, but it's easy to find them on the internet. So that got me initially interested. This Acorn User magazine had a program in BBC Basic where the initial image took about 8 hours to create. A few months later, they generated an assembly language version, which I think reduced the time to several tens of minutes. But those were the kind of times that you could expect the image to be generated on the screen. But it did get me interested enough to read that basic program on the BBC, convert it to a quick basic program in DOS. Because the machine I ran that on was significantly faster, I could generate those images in about somewhere between 2 and 8 minutes. So that was my first entry into these things called fractals. I then went to the university library, which I fortunately had access to, and tried to dig up a book which obviously at that age I was unable to understand. But the journey did continue. So I've been mentioning fractals. What exactly is a fractal? So there are really two, without going into the details, formal mathematics side, there are actually two very simple elements that they exhibit self-similarity. So you can actually see, if you take a sort of larger picture and then scale it down, it looks very similar to another picture. That becomes key in areas such as fractal compression. That's one of the uses of fractals, where you take an image and you actually reconstruct it by defining the geometric transformations. And the funny thing is that it doesn't matter what you give it as the original input. The transformations will eventually reach the image that you originally intended to. Those are usually very complex. They have lots of transformations involved to generate that image. The other thing is the dimension is non-integer. Now that we'll briefly get into in a moment. I don't know whether that's a relatively good size. This is just a timeline of sort of main events in and around fractals. Sort of the key element, I guess, is Manuel Mandelbrot coining the term fractal in somewhere around 1975. It wasn't about till 1980 where he first saw a picture of Mandelbrot set drawn. Things started quite a lot earlier. In 1983, the counter set, which if you take a line segment, take out the middle third, and then with whatever you've got left, you take out the third again and again and again and again. You get a very, very interesting construct, which sort of, you'll see a fractal which relates to it very well in a moment. The dimensions. Okay, so in 1918, Felix Hausdorff first mathematically defined this, how we were able to come up with this fractal dimension. Essentially, a point is a zero-dimensional construct. Line is one-dimensional. If you imagine a sheet of paper is two-dimensional, so you have two axes to be able to identify a point on it, and obviously 3 dimensions. The thing is, so fractals have dimensions that are halfway between one of those two. So if you imagine, for example, a crumpled sheet of paper is not quite the full box, but it's not just the surface. Maybe it will become a little bit more clear in a moment exactly what this fractal dimension means for us. So a few examples of fractals, and we start with, if you notice on the previous slide mentioned, there was an article on the determining the length of the coastline of Britain. This also in one of the books was published as the coast of Norway. But if you take any coastline, and depending on what is the size of the ruler, so these circles represent the how long is your measuring stick. As the stick shrinks, you get a constantly more accurate number. But how accurate? If you go down to atoms, will it be accurate enough or not? And it's this steadily increasing resolution that exhibits itself as a fractal dimension. There are a number of, there's a series of curves, this is the Koch snowflake, but there are a number of curves which sort of fold in on themselves, and they fill in a lot of space, but they're never actually completely that full sheet of paper. Those have a fractal dimension. We've obviously mentioned already the probably the most well-known fractal set, which is actually drawn, usually you see it in color, and it's drawn, the colors are derived from the rates at which certain functions reach, either stabilize or run off into infinity, for example. There are a whole set of fractals which are constructed by removing a component. So if you take the full square, remove the middle bit, then whatever you have left, you remove those parts again. And this here is represented in a Minecraft setting, both in 2 and 3 dimensions. This is the Menger sponge, by the way. L systems are a whole class of ways of defining natural structures like these. These are specifically dragon trees, but they're actually used quite heavily in computer-generated imagery. And here we're finally reaching the iterated fractal systems. So this is the Barnsley fern. What we see here, the light blue, dark blue, red, and also the green at the bottom. So we have a space which is being transformed, so scaled and rotated into somewhere very close to its space. If these transformations moved things far out, the drawing of this would sort of explode and travel off into a completely different space. So in order to draw this fractal, you would need to be able to scale and rotate your individual transformations. So obviously, iterated function systems, this is something that's, so the iteration comes from the repetitive process of it doesn't matter what point you start with, it will still draw you the image according to the transformations that have been defined. Thank you. Is there, just a brief, is everybody happy with understanding of 2 dimensions, what a coordinate and a vector is? It's the part of the demonstration that will, okay, so we get to the chaos game, which is one of the ways of generating the simplified class of those that do not require rotations. And this is the real interesting part that caught my eye many years after I tried doing the Mandelbrot set. I think at this point maybe not, we can use our imaginations. If we have 3 triangular points, we label them 1, 2, 3, 4, 5, 6, and we take a 6-sided dice, we roll that dice. Let's say we start from the middle, we will draw a dot halfway between where we are currently and one of those 3, depending on what the die tells us. We repeat this over and over and over and over again. That's effectively the chaos game as was originally defined. Now, what do you think will actually happen when we try this experiment? You could do this on a piece of paper. We will do it with a Raspberry Pi up here because it will just be faster. So do you think the dots will scatter everywhere if we have those 3 points and we can go halfway to them? Or will we fill in the whole triangle as the dots will be in that space that we've defined? Will a pattern of some sort emerge, or nothing really interesting? It will be a pattern. And are people, who actually knows the answer to this? What's going to happen? No? Okay, we will see it in a moment. It will be a pattern. What about 4? This is the point at which I sort of thought, well, now I need a program to be able to actually just explore this particular very simple game. Can I please switch to the...
What is that, HTML 2?
It is HTML 2, yes. Excellent, so we've done the... This is the two-dimensional version. So this is what will actually happen if we use 3 attractors. So the endpoints are called attractors, and we've started, I'm not sure where we started, we did have 1 stray dot there. We can actually reset that, and every time I'm regenerating points, I'm actually,
And what Raspberry Pi are you running there? Is that the Raspberry Pi 2?
This is the Raspberry Pi 2. I did try this on the Raspberry Pi B revision 1, my original one, which I have also in my backpack, and it was a lot slower. One thing to mention, I don't know whether we'll have time to go into the actual the snippet of Python code that generates this, but I'm generating 1024 points at each frame. There's another trick, which is the second part of the demo. So the next question was, what if we have 4 points? This program allows you to simply add more attractors. It generates just them around the circle. Obviously what's happening is it is actually just filling the whole sheet of paper. So nothing really interesting. But, okay, what about 5? Now we're starting to see something a little bit more interesting. It's not very clear. Maybe 6. 6, we're sort of getting almost a snowflake pattern in the middle. The reason I've used green is because the eye is more sensitive to green, so you can actually see the greatest depth. But if I pop up my information, so what I'm actually doing, 6 attractors, each of the weights, so move halfway toward one. The number of points, sorry, the color increase per point. What I'm actually doing, every time I place a point, I read the darkness of the point underneath, and I add a particular value. 256 means I go from completely black to bright green in 1 step, but I can reduce that and regenerate that image. It becomes a bit more subtle. It takes a slightly longer to generate, because obviously it's drawing those dots all over the place and brightening them up. But this kind of exploration, so I have seen programs which do what I've just shown you just 20 seconds ago. Mathematica has very good materials on it, but I have not seen these kind of density plots. This is my contribution to the to the topic.
So show you frequency of hits then on that point. Is
that?
Yes, it builds up the color based on the number of times. So we're effectively increasing the resolution depth-wise. We could actually also draw a much larger screen and then scale it down. That would be the alternative, but we'd use a lot more. Well, we use more memory if we went a single bit per pixel, but increase the resolution sort of 30 times the screen and then reduced it down. That's an experiment that's worth worth looking into. Okay, I think if we can switch back to the so the brightening of the color rather than drawing the dots directly was one thing, but I was thinking maybe there are other ways, and this is the part where it'd be interesting to actually sit down and try some other coloring strategies. I was thinking we're drawing them around a circle, in my case, they can be arbitrary. What if we drew them in star shapes? What interesting shapes would we get out of those? Obviously, we need to go from the simple mechanism of weights to actual affine transformations to do Barnsley's firm. And if anyone, this is roughly what the Mandelbrot set algorithm looks like, which is obviously no longer an IFS, but if you're just looking at it from the perspective of how complex is it to draw that colorful shape, and I think we'll end there. Thank you very much.
Thank you.